Hello, my name is Christopher Bennett, and I was a student at Carleton University in Ottawa, Canada, and I am here to present our paper titled Empirical Scanning Analysis of Censys and Shodan. Censys and Shodan are two prominent search engines for internet-connected devices increasingly relied upon by researchers and practitioners alike. Both Censys and Shodan enumerate the IPv4 address space and collect information about devices discovered. Upon conducting a preliminary empirical analysis, we provide insights into the following questions. How fresh are the results obtained from Censys and Shodan? How much resources can we expect to be consumed from the scanned devices by Censys and Shodan? And from the network's edge, how does the operation of Censys and Shodan differ? To answer these questions, we set up the following experiment. We used Amazon Web Services Elastic Compute Cloud instances to host virtual machines. We set up 5 virtual machines across the world, one in San Jose, California, Tokyo, Montreal, Paris, and Sao Paulo. The virtual machines were assigned a public IP address that remained unchanged for the duration of our experiment. Each machine ran 4 publicly facing services: FTP, SSH, HTTP, and HTTPS. The firewalls were configured with no restrictions. We collected network traffic on each virtual machine for 47 days, beginning on March 10th, 2020. After collection, we needed to identify Censys and Shodan traffic. We identified scans from Censys by using the publicly known Censys subnet. Shodan does not provide its source IP addresses. In order to identify traffic from Shodan, we used a DNS history search for the domain star.shodan.io. Any IP address that belonged to this domain is considered to be from Shodan. For our first question, how fresh are the results obtained from searching Censys and Shodan? To answer this question, we measured the time between when a service is updated and when the update is reflected through the Censys and Shodan's API. In our experiment, we focused on the freshness of the HTTP service. Each day, we generated a unique 64-character string, which we will call a token, for each virtual machine. We identified 3 time instances involving the tokens. The first one is the token change instance. This is the time that we updated the token and made it publicly visible on each VM. The token read instance. This is when Censys or Shodan read the token from our virtual machine. And the token visible instance. This is when the token became visible through Censys's or Shodan's API. Using these tokens, we calculated 3 spans. The read span, which is the time difference between the token change and the token read instances, the update span, which is the time difference between token read and token visible instances, and the refresh span, which is the time difference between the token change and the token visible instances. These 3 figures show CDFs of the read span, update span, and refresh span for the duration of our experiment for each engine. In total, we created 235 tokens, Censys captured 25 tokens, and Shodan captured 19. These charts are only showing the tokens that were found in Shodan or Censys's APIs. Our results show that both engines are fast to refresh the tokens once captured. All captured tokens were made visible within 24 hours of the token create instance. However, approximately 90% of the tokens were missed by each engine, suggesting that both engines could benefit from more frequent banner grabbing. Over the 47 days, each virtual machine received over 27,000 scans, 411 per day from Censys and 126 per day from Shodan on average. We focus on open port scans and banner grabs because closed port scans generate a small amount of traffic and are very quick. To answer this question, we measure the number of scans, the number of banner grabs, and how long they took to complete. Over the 47 days, each virtual machine received over 27,000 scans, 411 per day from Censys and 126 per day from Shodan. This heat map shows the number of open port scans received by each virtual machine. Censys has over 5 times as many scans on HTTPS as HTTP. Censys generated an average of 97 open port scans on each VM, and Shodan half that. This heat map shows the number of banner grabs for each service on each virtual machine. Like the port scans, Censys has a disproportionate number of HTTPS banner grabs. These charts show the duration of open port scans and the duration of banner grabs. We did not show closed port scans as almost all of them complete in under 1 millisecond. On average, port scans lasted 139 milliseconds for Censys and over 2,000 milliseconds for Shodan. The longest session lasted 248 seconds, which was an HTTPS banner grab from Shodan targeting the Montreal virtual machine. We looked into this session further and discovered the full banner grab was completed in 42 milliseconds. However, the final reset packet was delayed 248 seconds. Question 3. From the network edge, how does the operation of Censys and Shodan differ? We focus our comparison on the services both engines appear interested in, the pool of IP addresses used for scanning, and the configuration of the scanners. This table shows the 5 most commonly scanned ports from Censys and Shodan. The most commonly scanned port was HTTPS for Censys and HTTP for Shodan. Our data shows that Shodan's most scanned port, HTTP, came in 9th position for Censys. This figure shows the location of Censys and Shodan scanners. Blue circles represent traffic from Censys and red from Shodan. We can see that Censys scans from a single location in the US, while Shodan scans from multiple locations worldwide. Juan et al. Found that a single scan origin will miss 4% of HTTP and HTTPS traffic and 16% of SSH traffic. Since Shodan scans from multiple locations, it appears to provide a coverage advantage over Censys. The scanning origins figure shows the number of TCP sessions initiated from these locations. Here we can see Shodan scanned our virtual machines from 4 countries, while Censys only scans from the US. The distinctly contacted VM figure shows how many of our virtual machines were contacted by a distinct scanner. 40% of Shodan's 16 scanners contacted all our 5 virtual machines, and a third contacted only 1 virtual machine. The majority of Censys's 186 scanners contacted all our virtual machines. This shows what appears to be a fundamental difference between the configuration of both engines. Censys conducting more horizontal scans, whereas Shodan's scanners divide the IPv4 space among its scanners. The figure on the left and center show the number of ports each engine scanned across all our virtual machines. Here we can see Censys had many scanners scan a small number of ports, while Shodan had a few scanners responsible for many ports. The figure on the right shows the number of ports a scanner was responsible for conducting banner grabs on. Censys used 13 out of 186 scanners to conduct banner grabbing, while Shodan used 14 out of 16. This heat map shows the standard deviation of the number of hours between the start of each scan. We require at least 2 events to calculate the time between them. The empty cells are due to having a single corresponding event. Similarly to the previous page, this figure shows the standard deviation of the number of hours between the start of each banner grab instead of port scan. Overall, Shodan appears slightly more consistent than Censys for both banner grabs and port scans. We wanted to test if Shodan configures its scanners to scan nearby devices. This table shows the ratio of the average distance between Shodan scanners and each virtual machine, ADVM, to the average between the endpoints of observed TCP sessions, ODVM. A ratio of ADVM to ODVM close to 1 refutes the hypothesis that the geographic distance is a parameter in matching scan devices with scanner. A ratio larger than 1 suggests that the devices are contacted by nearby scanners, and less than 1 suggests otherwise. Upon further investigation, we found out that the anomaly with the Montreal VM is due to a nearby Shodan scanner being responsible for more traffic that is being sent to all VMs than other Shodan scanners are responsible for. We believe that Shodan does not base its scanning based on the proximity of the virtual machines. We analyzed the HTTP GET requests from Censys and Shodan. This table shows the user agents that Shodan used when requesting a resource from the HTTP service. Censys always used a constant user agent and the path /. In conclusion, our analysis on HTTP banner grabs shows that despite not capturing approximately 90% of our daily change tokens, remaining banners were made visible on Censys and Shodan search interfaces within 1 day of generating them. Shodan was slightly faster than Censys in grabbing new banners and in making them visible through its search interface. Based on our experiment, both engines can benefit from an increased banner grab rate, which complement their efficiency in making new banners visible. Upon analyzing resource consumption, one can expect to receive less than 40 banner grabs per month from each engine. Port scan sessions for open ports typically lasted less than a second, with Censys generally being faster than Shodan to close a session, especially for HTTP and HTTPS sessions. Banner grabs were slower, with many sessions lasting longer than 3 seconds. Finally, we noticed several differences in the operation of Censys and Shodan. For example, Shodan's scanners appear to be geographically scattered around the world, unlike Censys, whose IP addresses are all in Michigan, USA. Censys appears to be more focused on HTTP and HTTPS than Shodan, and it appears to dedicate a specific port to certain scanners and have other scanners probe many. I'd like to thank you for listening to our presentation, and now we will be taking questions.